Hello, hello, everyone. Let's do some shear and moment diagrams. I've got a simply supported beam here. I've got vertical loads, horizontal loads, and a line load. And the first thing we're going to want to do is our free body diagram. And let's see how I want to do this today. I think I'm going to just zoom in. I'm going to zoom in and just kind of draw up above there. So I have the beam. And the first thing I'm noticing is I've got a pretty large force, 25 kips upward here. I'm going to have a resultant force over here of 10. I've got 5 over here. So just looking at my forces, I've got net force going up. So I'm thinking maybe my reactions are pointing down for this one. And then I've got two forces that are equal in magnitude, parallel, opposite in direction. That is a force couple. And I'm just going to convert it into a couple moment, right? That's one of those statically equivalent systems. 2 times 4 is 8. So 8 kips times feet. And there is my free body minus the reactions. And see if my intuition's right. Let's go ahead and point these downward. A sub y, sub y. And now it's time for our equations of equilibrium. I'm going to do, we need some dimensions. We need some dimensions first. So I'm going to do a moment about A. And so, let's see. So this one is 2.5 feet. And the 25 is how far away? 10 feet. The 10 kip is, let's see, 17.5 feet. And then B sub y is 20 feet away. Okay, now I'm ready to do it. Summation of moments about A is equal to 0, and we're going to use a convention as counterclockwise positive and assume B sub y is down. Okay. First term, 5 times 2.5 sine negative. Next term, 8 sine negative. Next term, 25 times 10 sine is positive. Next term, 10 times 17.5 sine is negative, and the y are unknown, times 20-foot moment arm, and that one is negative. Set all of that equal to 0. Okay, and I'll go ahead and just run this through my calculator. Negative 5 times 2.5 minus 8 plus 250 minus 175 times negative 1 to move it to the right side of the equals, divided by negative 20 to isolate B sub y, and I get 2.725. I got a positive number, so that validates my assumption that that reaction is downward. Okay, for the next step, I'm going to do force equilibrium. And let's see how I want to do this today. Yeah, let's do, upward forces are equal to the downward forces. So upward, all I have is 25 kips, and downward I have A sub y unknown. I have 5 unknown, known. It's been a long day. 10 downwards, and I have b sub y downwards, which I just solved for, which is 2.725 kips. And since I've got that in my calculator, I'm just going to say plus 15 times -1 plus 25, and I get a sub y equals positive 7.275 kips. Assume a sub y equals downward. So that positive sign in our result just validates our assumption. So we have our reactions ready to go, and I am just going to put them back into our beam. 2.725. Okay, I think that's looking pretty good. I'm going to make one other change. I'm going to go ahead and take out all of this mess and replace it with that couple. Okay, so I'm just going to replace that with my couple, statically equivalent system, and 8 kips times feet. Right, looking good, looking good. Time for shear and moment diagrams. First thing I always do is label the plots so I don't forget. So V, and include the units, units of kips, moment, units of kips times feet. Start our shear diagram, start at 0, follow the direction of the arrows. So subtract 7.275. And I'm writing down 4 sig figs because I want that precision as I do the next step to create the moment diagram. And then I'm going to decrease by 5. And I'm going to go ahead and write down a 5th sig fig. If you round to 2, that would be okay as well. But putting in a 5th there is still reasonable and effective ways to communicate. Okay, we go all the way over here. We increase by 25. And the reason why I'm throwing in the 5th sig fig at my discretion is because all the digits after that are 0. And so I can use precise numbers. And therefore, when I finish up my moment calculation, I love when my calculator says 0.000000 E0. Love that. All right, let's continue over 5. And now I want to decrease by 2 times 5 is 10. That gets me to positive 2.725. And then lastly, decrease back to 0. Okay, so I got back to 0. The only function that's missing, right? So I had a 0, 0, 0, 0, which is why these are constant, 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 constant. And here I have a constant that integrates to linear. And so I'm going to use a straight line to connect those 2 dots. Wrong color. There we go. Shear diagram, fantastic. look good. Time to do our moment diagram. Zero out my calculator. Okay, start at moment equals 0. And at this point, I go back and I scan my loading diagram. And this is what I'm on the hunt for. Any type of couple moment. So it could be a couple moment load, could be a couple moment reaction. And so I'm just gonna put a little reminder to myself when I get right here. I'm gonna have to jump. And I'm drawing it through the shear diagram intentionally. What that means is when I go to compute the areas, I kind of split this up into some different shapes. When I go to compute the areas, I'm gonna have to do that separately than that because I'm gonna have to jump once I get to that moment. Okay, I think we're ready to go. So I'm starting at 0. My first area is negative. So I put in a minus sign. And then I multiply the height of the rectangle, 7.275, times the base of the rectangle, 2.5. And that gets me to negative 18.2. And I've already worked this solution. I know I'm going to need a lot of negative real estate. So that's why I'm making that so subtle if you're wondering why. Okay, constant integrates to linear, so we'll do a straight line there. All right, our next area, so it's negative. So we do minus sign for negative. The area has a height of 12.275, and the base is 2.5. So that takes me down to about here, 48.9. 3 sig figs, and that final answer is fine. And how am I going to get there? Constant integrates to linear. So just a straight line between the two. Now I'm ready to jump with my 8 kip feet, and I have to remember the rule that all the static students hate. Clockwise, jump up. Like there's a clock on the wall and you want to like jump up and pat it. And counterclockwise, jump down. So look down and there's a counter, reach down and pat that. So however you want to do this, figure out a way to memorize and apply that. So for ours, our moment is clockwise, and so we jump up. So we add 8 kip feet. That increases just a little bit to 40.9. And when you're doing this, like if you're in my class, I know not everyone watching the videos in my class, but if you're in my class and we're in an exam or a project or quiz or homework, make sure you calculate and label all values. And I know it's easy to get lazy, especially if you're just using a calculator the way that I am in this long running calculation. But still, please label them all so that we can assess you fairly. All right, and now it's business as usual. So we decrease by that area. So minus 12.275 times 5. Okay, how do we get there? Constant integrates to linear. So we do it with a straight line. Yeah, close enough. Okay, Our next area is a positive, so we do plus 12.725 times 5. Okay, and that gets me up to negative 38.6. Constant integrates to linear. So do that with a straight line. Okay, and now I have one final bit of increasing to do. And I could either use the formula for a trapezoid. The formula for the trapezoid is multiply the average height by the base. But I'm going to simplify my calculator calculation. So I'm going to add the rectangle, and then I'm going to add the triangle. Okay. And I'm going to remember that this change from here to here was, oops, sorry about that, was equal to 5 times 2. So there is my 10 of change, 10 kips of change, and use that for that triangular area. All right, let's go ahead and do it. So let's add in the rectangle, which is 2.725 times 5, and then add in the area of the triangle, which is 10 times 5 times 0.5, and lo and behold, we get back to 0. Please, 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 always do the last calculation, because if you don't get back to 0, you got an error, and everything you have done is super messed up. You fix it. All right, there is my lovely, lovely moment diagram, and equally lovely shear diagram. And that's it for this problem. Thanks for tuning in. I hope you enjoyed it.